Chairman. I am Esteban Cabanillas, a research engineer from CEA-Leti, and I'm going to present this work named Ultrasonic Sensor for Pipe Joint Makeup Assessment. So the result presented here, okay, thank you very much. The result presented here comes from the collaboration between the department system of CEA-Leti and the society Vallourec. So the planning of the presentation, firstly, I'm going to introduce the pipeline system developed by Vallourec and the way it is deployed. Then a method based on piezoelectric transducer used to test the clamping state of the pipe will be presented. The third section deals with the heteroline technique used to implement that method. The electronic prototype and the performance of the prototype are described in section 4. And finally, section 5 concludes this presentation. So as I said before, the target of this work are the pipelines, and more precisely, the offshore pipelines. Pipelines are composed of various kinds of pipes, generally named OCTG. We can differentiate 3 kinds of OCTG. The first one are the drill pipe. Drill pipe are used to perforate the solid layer under the sea. Then we have casing pipes used to stabilize the complete structure. Inside that case, we can find tubing pipes. Tubing pipes are transporting fluids like gas or oil. The Vallourec tubing pipe is installed by connecting pipes with coupling elements as, sorry, I don't have the point, as the one you have here, at the coupling element. So this coupling system is the object of this work. Here we can see the VAM coupling technology of Vallourec. The sealing of the system is done thanks to metal seal. The sealing is confirmed when the pipe pin is in contact with the coupling limit stop. On-site operations are done with torque measurements. The operator checks the torque still reaching the target value. The main issue with this torque measurement is that we cannot be sure about the contact between the pipe pin and the coupling limit stop. So the remaining of this work deal with that problem. How can we verify that the contact inside the tube is well done? So the contact sensing shall be done with some conditions. We cannot do holes, or we cannot put cables through the metal. We cannot put active electronics or batteries inside the tube because of explosion risk. And the system inside the pipe shall be installed in the internal surface without disrupting the rounded shape, the rounded shape of the tube. So the method we propose to know the contact state of the pipe is by ultrasound propagation through the metal, using piezoelectric transducers. The main idea of our technique is the transmission of energy by aligning a pair of piezoelectric transducers on opposite side of the pipe, just like a sandwich. A continuous wave excites the outside transducer, and the acoustic wave is received by the internal transducer. So the challenge is to get the information inside the tube. Our solution focuses the study of the input impedance of the coupled system. For the following demonstration, the contact or not contact state is replaced by an on-off switch here. So we are going to study the input impedance firstly with the switch open. This is the not contact scenario. With current I2 equal to 0, the open circuit input impedance is the set parameter Z11. We make the same for the switch close scenario representing the contact state. So with V2 equal to 0, I2 is defined as a function of E1. Then the input impedance for short circuit scenario is defined as follows, as you can see. Then it is interesting to compute the difference between open and closed scenario for the input impedance. So we have here the formula. If the coupling between piezoelectric is high enough, this is the case for the resonant frequency of the piezoelectrics. The product set 1 to set to 1 is also high. So we have a strong variation of the product when the switch state change. So the trivial way to test if the contact between the pipe and the coupling is well done is by measuring periodically the input impedance, and we stop measuring after detecting a high variation of the input impedance. But it could be too costly in terms of manpower. So the third section introduces a new technique that we developed. With this technique, we need to check only once the input impedance value just after clamping. So we add to the inaccessible side a couple of anti-parallel diodes. For this demonstration, we can make the value of V1 variable. We can have a gain low or gain high. So the technique is making 2 steps. For the first step, the gain is set low. Then V2 is lower than the diode threshold voltage. So the current through the diode is 0. Then the input impedance is a function of the switch steps. For the second step, we set the gain high. The voltage V2 is bigger than threshold voltage for the diodes, and the diodes are in current condition. So for this scenario, the input impedance is that of switch closed case, independently of is that of short circuit, independently of the switch. So the contact test is good if the input impedance with low gain is equal to that of high gain. The method we implement can measure phase or module of the input impedance. For this case, we choose to study the phase because Gaussian noise reliability reasons. So this method had been patented 2 years ago, and now we are presenting that. Next, I will show you the electronic system we developed to measure the input impedance. So this is a heterodyne system. We have a digital standardizer generating a sinus signal, and then we have the variable gain amplifier. That digital standardizer generates signal V1. Then we get indirectly the image voltage of the current VI thanks to the shunt resistor R here. VI is an image of V1 with a phase shift of phase phi, and that is the phase that we want to measure, the phase impedance. The voltage and the current voltage are in quadrature multiplied. The quadrature shift over V1 is done with a shift integrator filter, 40 degrees block. Then we implementate low pass filtering. We have signals L1 and L2 that are a function of the phase phi. These signals are then converted to the digital domain with ADCs. And then an arctangent function of the ratio L2 and L1 gives the phase impedance. Next, I will present the implementation of this technique. So for the test, we get a Vallourec pipe and coupling system, and we develop a tester, hand-size tester, using just commercial electronics. For the tester, we use an STM32H7 microcontroller, and we also use an analog device, digital standardizer. So here we have some system views of the system. You have here the tester. The contact between the tester and the pipe is done with pogo pin. That pogo pin touch a PCB which is directly connected to the external side bias electric. An additional view with the section of the system. Here you have the tester, the coupling, and the pipe. So you have here the needles of the tester with the PCB and the bias electric, the external side, And the internal side, again, with a piezoelectric with the PCB. And we have two needles who touch the pipe when it is completely clamped. This needle acts as the switch of our demonstration. An additional view with the internal side of piezoelectrics. This is the circuit one. We have the anti-parallel diode, and here the needles that put the piezoelectric in short circuit when it is in contact with the. Next, the simulation results. Firstly, to validate our tester, we compare our result with a vector network analyzer. So here you can see the variation of the phase with respect to the frequency with a span from 4.3 to 4.7 megahertz. You can also observe different phase variation with the system, which it is in contact state or open, contact state or closed, and with the system closed. As you can see, the VNA results are almost similar to our tester. So the frequency scan is also used to find the good frequency to effectuate later the contact test. So this is the resonance phase. You can see that here. That is a frequency that presents maximal coupling between the piezoelectrics. Then I effectuate the test with this frequency. As I explained before, the test is done in two steps. The first one, the gain of the signal, the signal is set high, low, and then high. So the test for no clamp or not contact scenario shows a phase difference of 10 degrees. Note a little problem. We have when the amplitude is high, and actually we are attending something for minus 40 degrees. So that's an issue that we are going to study for future works. And here the results for high gain scenario. So the difference is only 2 degrees. That was the expected value. So it is possible to discriminate the contact state with this relatively high differences in phase. So some conclusion, we have proved that the potential of piezoelectric transducer for pipe clamping test. The system uses only passive electronics in the internal side of the tube, just commercial electronics for the tester. I propose some results showing a notable difference of phase between the clamp and not clamp scenario. So some challenge for the future. So the first one is to improve the quadrature filter that is not wideband. We use just a shift filter which has 90 degrees just for one frequency, and if we are not at that frequency, the shift is not quadrature one. Then we need to study that problem that we had with the high gain condition. We didn't have the behavior we expect, but we had everywhere a good measure. And the final proposition is to work with a full digital solution to improve precision and also the test time. You must know that the test for clamping test is around 10 seconds, and we would like to do that in a fraction of a second. So thank you very much. Please, if you have any question.